A crimson web drifts past, blood-red flesh that here is all but invisible. Sunlight has vanished 1,000 meters above, so creatures like Vampiroteuthis have evolved colors and forms unchanged since the age of fossils. Down here, bodies shrink or glow, preserving secrets older than dinosaurs. But why does the deep force life to turn so prehistoric? And what ancient rules shape everything we are about to encounter? Red vanishes first. Even at 20 meters down, the ocean starts to erase it, stripping away every warm hue until only blue remains. By the time you reach the mesopelagic zone, sunlight is filtered to a single, icy wavelength, and everything else is swallowed. For creatures like Vampiroteuthis, that blood-red webbing is the perfect cloak. In this twilight, red does not glow or stand out. It disappears entirely, turning flesh into shadow. Predators and prey drift past, blind to anything painted in vanished colors. Here, camouflage is written in physics. To survive, bodies blend with the dark, and only those who master the art of invisibility endure. A flicker cuts through the blue, a cold, living spark. Down here, sunlight has vanished entirely. In its place, deep-sea creatures make their own light. The anglerfish drifts, its lure glowing with a blue cyan shimmer, powered not by the fish itself, but by colonies of symbiotic bacteria packed inside the esker. This borrowed light is more than a trap for prey. It is a language and a beacon. Eyes in the deep are tuned to catch these faint glows, filtering out everything but the narrowest band of blue. In a world without sun, life engineers its own answers to darkness. A shadow glides past, mouth half open, teeth like needles set in velvet. The frilled shark, with its eel-like body and ruffled gills, looks like it slipped out of a Devonian fossil bed. Its jaw hinges wide, lined with rows of backward curving teeth, almost identical to fossil sharks that hunted in the seas 80 million years ago. This is not just a trick of old bones. The living animal carries the same silhouette, the same ancient machinery for snaring prey in the dark. In the deep, body plans do not need to change much. Survival here means holding on to what already works, even if it is a blueprint from a forgotten era. At nearly 8,000 meters, the Hadal snailfish glides where no other vertebrate survives. Every cell inside its body is braced against pressure that would flatten most life over 800 times the force at the surface. The secret is TMAO, a molecule deep-sea fish stockpile like invisible armor. In the laboratory, scientists place snailfish enzymes in high-pressure chambers. Without enough TMAO, those proteins collapse and lose all function. But as depth increases, so does TMAO, rising in a near-perfect line, millimole by millimole. There is a catch. Beyond about 8,200 meters, even TMAO cannot keep up. The chemistry reaches a hard stop. No vertebrate has ever been found deeper. A pale shape drifts just above the seabed, moving with the patience of centuries. The orange ruffy, a deep sea fish with a lifespan that can stretch beyond 100 years, glides as if time itself has slowed. Its heart beats at a fraction of the pace seen in surface dwellers, every movement measured and spare. Food is scarce here, and each meal might be the last for weeks. Giant isopods, armored and ancient, crawl in low motion, conserving every scrap of energy. In this world, survival means slowing life to a crawl. The price of endurance is vulnerability. Grow slowly, reproduce rarely, and any wound or loss takes decades to heal. No vertebrate has ever been found below about 8,200 meters. The reason isn't just pressure, it's chemistry. To keep their proteins from collapsing under the immense weight, deep-sea fish must pack their cells with TMAO, a molecule that acts like invisible scaffolding. But there's a limit. Beyond roughly 8,500 meters, the amount of TMAO needed would push the cell's internal saltiness above that of seawater itself. At this point, water would rush out of the cells, and basic life processes would fail. This osmotic barrier draws a sharp line. Vertebrate life hits a wall, and only invertebrates continue deeper. Clouds of superheated water billow from cracks in the seafloor, swirling with minerals that would poison most life. Yet anchored to these vents, riftia tube worms grow in dense, waving forests, white plumes reaching into the chemical-rich water. Here, sunlight is a rumor. Instead, bacteria inside riftia's tissues harvest energy straight from hydrogen sulfide, turning toxic gas into food. Every animal in this community, from shrimp to clams to crabs, owes its survival to these unseen chemists. This is a world powered by geochemistry, not by the sun. The vent fields echo Earth's earliest ecosystems, running on the same molecular engines that fueled life before photosynthesis ever began. The coelacanth, Latimeria, glides through shadowed caves, its armored scales and lobed fins unchanged for hundreds of millions of years. Genetic analysis confirms this is not just appearance. Molecular clocks date its lineage's split from other vertebrates to nearly 380 million years ago. The living fossil swims on, a direct link to the Devonian seas. Here, evolution slows but never stops. As deep-sea mining expands, what survives isn't just ancient, it's vulnerable.